আচ্ছা, Hertzsprung-Russel diagram to relate luminosity and temperature. Use this diagram to explain the life cycle of stars. So first of all, Hertzsprung-Russel diagram জিনিসটা কি বুঝতে হবে, and from there we can move on to how, like, we can work with it. So let's first, if we Google it, কি কি আসে দেখো, we get these nice diagrams. খুব সুন্দর সুন্দর কয়েকটা diagram আছে এখানে, and এখানে for example we could take this as a good idea, right? এই যে diagramটা আছে এখানে to represent a HR diagram. So let's see the properties of an HR diagram. So we get the graph's axes. This is temperature versus luminosity. So obviously what we do is, once we identify a star, যে কোনো একটা star, তারপর আমরা এই diagram মধ্যে এটা plot করে ফেলবো. So that's what we've been doing. We've been plotting thousands and thousands of stars along this graph of luminosity versus temperature. ঠিক আছে, এরকম করে plot করা হচ্ছে. So yeah, এরকম করে we see that there are different regions. এইদিকে দেখো, এই সাইডটা, if you look at the diagram from a distance, we can see there are different regions. There's এই পাশটা, the left side is kind of like, short wavelengths, which is blue. ঠিক আছে, as you move towards this side, it becomes longer wavelengths, which is red. So এটা we can relate it to the temperature based on Wien's law, right? কি বলে? That lambda max into temperature is equal to 2.898 meter Kelvin, right? So ওইটার উপরে বেস করে তো যদি তুমি বলো, so what do we see? We see that obviously as the temperature decreases, the wavelength, the most highest intensity wavelength will be longer, right? And if you go to this side, the temperature is higher, it's shorter. So এখানে দেখো, couple of things I would like you to notice. Number one, the scale is logarithmic. ঠিক আছে, so 4,000, 40,000, তারপর 20,000, 10,000, 5,000, 2,500, মানে it's a logarithmic scale এইদিকে। ঠিক আছে, আর এইখানেও গ্রাফটাও it's exponential, 10, 10 power 2, 10 power 4, 10 power 6, ঠিক আছে, কত জানি দিছে। So এরকম করে তোমার you will have to use these sort of diagrams. ঠিক আছে, so now let's try to plot this sort of graph, at least draw it up and try to figure out what it's all about. So we can draw a very simple HR diagram. Yeah, that's mine. Assalamualaikum. जी কি আজকে? আচ্ছা, আমি তো বলতে পারতেছি না ঠিক, হয়তো বা ভুলে ভুলে যেতে পারে আর কি। নাম্বার কি কয় না কয়। Alright, তারপরে so yeah, say we can plot a graph like this. So graph এই পাশে is going to be temperature, right? কিন্তু টেম্পারেচারটা কি হইতেছে? It's decreasing. So decreasing temperature, if we consider Wien's law, ঠিক আছে, T into lambda max is equal to 2.898, right?
Yes.
So we can say that they're inversely proportional to each other. So decreasing temperature means what? Increasing wavelength, right? So this is like wavelength. আর এইদিকে যদিও এক্সপোনেনশিয়াল হবে, আর এইদিকে এটা হইতেছে কি জানি, luminosity. ঠিক আছে, luminosity, আর luminosity এখানে কি ইউনিট জানি ওরা ইউজ করে, it's in relation to the sun, বুঝছো? মানে luminosity versus the sun, luminosity of a star versus luminosity of the sun. So এরকম, so yeah, the sun's luminosity would be here 1, ঠিক আছে, এর চেয়ে কম হলে এদিকে হবে 10 power, say like something এরকম করে। So these graphs usually go to values like 10 to the power -4 or -6, এরকম 10 to the power -6, আর ওইদিকে obviously ওইটা এদিকে উঠতেও পারে, উঠতে it goes all the way up to 10 to the power 6. And a temperature, they expect you to know range of the temperatures for the x-axis. So like usually this value is anywhere from like 36,000 to 40,000 Kelvin, ঠিক আছে, and তারপর যেটা হয় তোমার দেখবো যে একটু এখানে এসে it becomes 20,000, তারপর একটু এদিকে এসে it becomes 10,000, তারপরে it spreads out অনেক wide করে, এখানে এসে 5,000. This is what logarithmic graphs look like, ঠিক আছে, 2,500. The reason we do this is because the range over which the temperature range that we have to plot on the graph is really wide. এরকম যদি আমরা গ্রাফ প্লট করতে যাই যেটা লিনিয়ার স্কেল হতো, it would be like really long and it would be really ridiculous. এক জায়গায় দেখতে অনেকগুলো স্টার, আর পরে আস্তে আস্তে ছড়ায় চিটকায় না হয়ে যেত, right? So we don't actually draw it like this, we draw it with a logarithmic scale, it's easier to represent. So এরকম একটা প্লট করা হলো। Now if we just have a small and quick overview on the graph, we see a couple of things. কি দেখবো আমরা? We'll get high luminosity stars on this side. Sorry, we'll get high temperature stars on this side. ঠিক আছে, কারণ দেখো high temperature এরকম, and we'll get low temperature stars on this side. So high temperature হলেই আমরা কি জানি wavelength short, so obviously we're going to get blue stars on this side and we're going to get red stars on this side. এটা গেল blue red এই ব্যাপারে। আর আমরা এই axis এ যদি ধরি luminosity, if we talk about Stefan Boltzmann law, right? Stefan Boltzmann law টা বলো তো, what was it? Luminosity is equal to
the Stefan Boltzmann constant, the
sigma into surface area, which if it's a sphere then it's 4 pi r square
and temperature to the power 4.
T to the power 4. Yeah, so this is Stefan Boltzmann law. I recall this কত বড় 3-4 বছর পরে রিকল করছি।
ওটাতে into 10 to the power -3 হবে আর
oh dear, oh হ্যাঁ এখানে -3 ছিল 2.898 anyway তাহলে আমরা এটা কন্টিনিউ করি, ঠিক আছে? So this is Stefan Boltzmann law. So based on this, the luminosity আমরা কি দেখতেছি, large stars will naturally have high luminosity, right?
Yep.
And small stars will have lower luminosity, and obviously যত গরম তত বেশি temperature বেশি লাগে। So এইদিকে you're going to get what? Large stars, and here you're going to get smaller stars. So এইখানে দেখো আমি চারটা quadrants করছি, ঠিক আছে? So what would we get in these quadrants? You'd get a very typical star here, ঠিক আছে, যেটা not too large, not too small, ঠিক আছে, not too red, not too blue, ঠিক আছে? So this is where usually our sun is, ঠিক আছে? বাকি জায়গায় কি কি পাবা? এইদিকে আসলে in this region what you're going to get is stars which are large but cold. Do you get this? এই রিজনে এই কোয়াড্রেন্টে you're going to get stars which are large but cold. এখানে কি পাবো বলো তো? এই রিজনে small but cold, right?
Yep.
আচ্ছা, এই রিজনে কি পাবা? Large and hot, right? আর এর নিচেটা কি পাবা? Small but very hot. So yeah, let's make some assumptions. For example, something which is you could say কি বলবো, really low temperatures, ঠিক আছে, and তোমার over a range of values of size, ঠিক আছে, that would be your nebula, ঠিক আছে? Nebula মনে আছে না? The cloud from which stars are created, right? So your nebulas would be around here. মানে stuff that stars are created from really low temperature. Does that make sense? Nebula ছোট হইতে পারে, বড় হইতে পারে, অনেক রকম হইতে পারে। গেল where would we get red giants? Red giants, obviously it's going to be red because temperature low and giants, right? So this is the region where we're going to get red giants. Where would we get stuff like blue supergiants? Somewhere around here, right? ঠিক আছে, এরকম। তারপরে হইতেছে where would we get white dwarfs? White dwarfs would be somewhere around here, ঠিক আছে, based on like এখানে কেন হইতেছে, because luminosity is going to be low, the temperature is going to be really high. এরপরে কি হবে, white dwarfs as they cool down, which way would they shift? They would shift down along this. কেন? কারণ এখানে এসে আস্তে আস্তে তোমার temperature কমতেছে and everything. So এটা হইতেছে based on like where we expect things to be. And what about all the other star classes? ঠিক আছে, ওই O class থেকে M class পর্যন্ত, বুঝছো? ওই স্টার গুলো তোমার কোথায় কই যাবে? So what's going to happen is আমরা যদি stars নিয়ে just randomly আকাশ থেকে দেখে আমরা যদি ওটা luminosity versus temperature plot করা শুরু করি, we kind of start getting a graph, ঠিক আছে, a plot, scatter graph বলে বা যে plot বলে, and it looks something like this. এই যে এরকম আস্তে আস্তে there's a sort of trend, এরকম একটা trend আসে, ঠিক আছে, and it looks like this, বুঝছো? Each dot would represent a star. আর এই যে গ্রাফটা, এই প্যাটার্নটা আসছে, ইটস নট আ প্যাটার্ন যেটা আমরা আগে প্রিডিটারমাইন করে তারপর গ্রাফ প্লট করছি। দিস ওয়াজ অ্যাকচুয়ালি আ প্যাটার্ন দ্যাট উই স আফটার উই প্লটেড অল দ্য স্টার্স, ঠিক আছে? সো হোয়াট ডাজ দিস শো? This shows a very common trend that you should know. Stellar evolution থেকে তোমার যদি ভালো করে জানা থাকে, that if the temperature is really high, how are stars burning at high temperatures? It's because the star is very massive and the core has a high rate of fusion going on in it. Yes, the fusion rate টা খুব high. So high rate of fusion money হইতেছে that the temperature will be high, right, over the surface and also all of that. So how can you do high rates of fusion? You have to have huge pressure and temperature, right? Density and all of that. So to create that you need high mass stars. So temperature high হবে কার? High mass stars, right? High massive stars, very massive stars. So that's why high temperature stars এরকম হবে। As we look at the classes and we see over progression যে আস্তে আস্তে তোমার স্টার এর ম্যাস যদি কমতে থাকে, স্টার ক্লাস দেখলে আমরা কি দেখি, স্টার ম্যাস যত কমতে থাকে সারফেস টেম্পারেচারও তত কমতে থাকে, রাইট? সো ওইরকম আমরা কি দেখতেছি যে as the mass decreases তখন luminosity will also decrease কেন surface area কমবে and সাথে temperature কমবে because the rate of fusion is less, right? Does that make sense? So এটা আস্তে আস্তে কমতে থাকে and at a point we come across the sun is going to be anywhere around here, like orange yellow region. Some places, it depends on how you draw the graph, you can get it somewhere around here also. It doesn't really matter where, but the sun is going to be what we call a main sequence star, because it lies on this sequence. A sequence টাকে বলা হয় the main sequence, where all of the usual stars are. When it's doing normal fusion fission, abnormal পাগলায় মরে যাচ্ছে যদি তখন গিয়ে red giant, blue super giant এইসব হয়ে যায়. But if it's a typical star, everyday star, তাহলে main sequence. So compared to other stars, our star is very typical, very pathetic, very everyday. So it's the guy that you won't remember from high school.
Yeah.
When you're very, very, that's you, that's it. Anyway, so don't be sad. So তারপরে কি হইতেছে? If we take stars around here, তাহলে এগুলো হইতেছে very sun-like stars. So their mass is close to the mass of the sun, luminosity is close to the sun, temperature is also close to the surface temperature of the sun. So এখন this is where we would get the sun and everything, and if we were to go to less massive stars তখন কি আমরা কি দেখবো যে obviously luminosity কমে যাবে, surface area কমতেছে, temperature কমে যাবে, so দুইটা কমে, we get them at lower values. Does this make sense?
Yep.
All right, so এই গেল তোমার Hertzsprung-Russel diagramমের layoutটা. If you understand this layout, I believe you'll be able to understand any of the HR diagrams. This should make sense now. We have the main sequence, we have red giants, red supergiants, blue giants, white dwarfs, and main sequence shifts from blue all the way to red. White dwarfs are white. So yeah, there's lots of really nice diagrams. Whatever you Google, you'll come across these nice diagrams here. They didn't give the dwarfs and stuff, but they have all the other stars. So they've plotted a lot of stars here, and somewhere around here you can expect the sun. Alright?
Yeah.
Okay. So moving forward. HR diagram how can we use the HR diagram? So HR diagram use করা যায় দুইটা জিনিস করার জন্য. Number one, we can use the HR diagram to figure out if we just look at a star's temperature, we can make an estimate of its luminosity. So this is a very rough way of doing it, but it works. And we use this with a process called standard candle. Standard candle
Yes.
Standard candle, we'll talk about it. So standard candle is basically you have to estimate the luminosity. That's one of the first steps. Luminosity, you can figure out how far the star is. So the first thing we can do is we figure out what the value of lambda max is. Ekta star theke je light ta ashteche, oi light theke amra lambda max ber korlam, lambda max theke amra temperature ber korlam. Temperature ber korar pore, if it's a main sequence star, we can make an estimate of its luminosity. So this is how the HR diagram comes in very handy to figure out the standard values. Or it acts as a standard for finding out the temperatures of stars, finding out the luminosity of stars from which we can use to calculate the distance. This is one place on the HR diagram that I like over. HR diagram knowledge is how, as stars go through evolution, it's stellar evolution, how they shift around the HR diagram. So yeah, first of all, we're going to get what? Planetary nebula, or basically planetary nebula. We're going to get nebulas, right? So nebula হলে তোমার যে জিনিসটা হবে এখানে nebula. What happens is, if these collide and create stars, তোমরা তো stellar evolution দেখছো যে fusion হয় কেমনে, because you have these massive clouds of hydrogen, they collapse on themselves and start the process of fusion in the core. When this process starts, what do we call it? We call it a protostar. So protostars obviously will have higher temperature, and luminosity also একটু বাড়বে. So nebula থেকে যখন a star is born, it shifts এরকম. So you would expect protostars to be around here. মাত্র জন্মাইছে. So এইখান থেকে, if it's a very typical star, then it's going to shift into the main sequence. Alright? Main sequence গেল. Let's consider our sun. So the sun is going to be around here. এখানে তোমার main sequence protostar হয়ে চলে আসলো. তারপর sun fusion হইতেছে. What's going to happen to the sun after the fusion after a certain amount of hydrogen decreases? 80% এর নিচে চলে গেলে কি হবে?
It expands.
Yes, and it turns into what? A red giant. So red giant হলে কোথায় যাবে? It will shift from here all the way into this region, right? আস্তে আস্তে a red giant shift processটা যখন হবে তখন কি আস্তে আস্তে কি হবে? Or temperature fall করা শুরু করবে, but it will expand. So hence it's going to shift into the red giant region. তারপর red giant হওয়ার পরে কি হবে?
Red giant হওয়ার পরে it starts fusing helium inside it.
ওই সব হিবিজিবি হওয়ার পরে it starts ripping off its surface, layers চলে যায়, তখন it creates what we know as a planetary nebula. ঠিক আছে? And outer layers they fall off, right?
Yep.
They're thrown off, and we're left with the core, right?
Yeah.
So if the core is small enough, then what do we get? We get something which collapses again, right? And makes this high temperature, high density mass, which cannot fuse. Current fusion or sufficient mass. So that is a white dwarf. So as the star rapidly collapses, it will move from there to here. So this is your white dwarf region. So this is where you can expect white dwarfs to be. Over many billions of years, the white dwarf will cool down. Cool down it will shift and become eventually a black dwarf. White থেকে red হবে, red থেকে তারপর আস্তে আস্তে orange মানে white হয়ে red হবে, তারপর শেষে it will become a black dwarf. Can any of you guys tell me why don't we have any black dwarfs in the universe?
The universe is not old enough.
Very good, because the age required for the yellow stars, for the dwarfs to actually cool down to black dwarfs, is not long enough. The age of the universe is not old enough exactly to let something like that cool down yet. We'll expect that in the future. Done? HR diagram, what's up?
Yes.
So yeah, that's it. That's the HR diagram right there.